Today, we are not gonna cover very technical stuff, but we will discuss what virtualization is, what VMware is, what cloud is, how cloud was built, and what are the advantages of the cloud. We're not gonna log into any cloud portal. We are just discussing how this evolution begins and what are different type of virtualization and what we are doing with our laptops. Like I am running VMware Workstation. Some of you are running VirtualBox. So these all are the hypervisors. We call them hypervisors. There are two types of hypervisors. Type 1 hypervisor, which we call the bare metal hypervisors, and there are type 2 hypervisors, which are called hosted hypervisors. So what we are working on right now, these are hosted hypervisors. Like they are hosted on some operating system. Like I am running Microsoft Windows, and on top of it, I am running a hosted hypervisor VMware Workstation. On that VMware Workstation, I host multiple operating systems like VMware, Microsoft Windows, like Linux, like RHEL, CentOS, Ubuntu. So our OS is managing the hardware resources, and these hardware resources are then presented to our hosted hypervisor, and then it provide those hardware as a virtual hardware to the hosted hypervisor. So let's discuss it on the board that how we are gonna differentiate both of them. This is our box or our laptop, or generically we can say this is our hardware. And on that hardware, we have our kernel, or what we can say on that hardware, we have our operating system. That can be Mac, that can be Windows, that can be Linux. Under that OS, we have kernel, and then we have applications. And one of the application is the hypervisor. So what our kernel is doing, it is managing our CPU, RAM, disk, network, SCSI devices, and everything. And we all know that when our applications run, they require CPU cycles, they require RAM, and they require disks. So all those things are presented to our application. Application can be Word, it can be Zoom, it can be anything. So these hardware resources are provided to these applications via kernel. And same is the case with our hypervisor. So our hypervisor requests CPU, RAM, and the kernel provides it. And what hypervisor does is it creates a virtual machine. Virtual machine has its own kernel on OS, and on top of that OS, we have our apps. We run the second machine. It has its own kernel, OS, and we have our apps, and so on. We have our hard disk available here. The CPU is given to this hypervisor, and that hypervisor gives CPU to these apps and this kernel. And same is the case with this. Actually, this kernel provides it to these apps. Why we are going into the virtualization world? I mean, it started in back in late 90s, because the CPU speeds are increasing every year, probably doubling every year. We have a lot of RAM available. We have very big machines coming. Even our laptops CPU is mostly idle. That's why we are running 4, 5, 6 machines on our laptop, because the CPU is so much that we don't actually need it. And if we are talking about servers, so we have in our laptops we have one socket available. One socket is like one CPU. It's like this is my hardware. I can have 4 CPUs or 4 sockets available. Every socket can have 32 cores. Like on a hardware level, we have, just like in our laptops, we had earlier days, we have dual core, core 2 duo, core i3, core i5, core i7. So this CPU is logically divided into 32 virtual sockets, virtual cores. And there is a concept of hyperthreading. So this 32 is further divided. Every single core is divided into then 2 cores logically on a hardware level. So now what we have is 32, 32, 32, 32. We have 128 physical cores and 256 virtual cores. And if the clock speed is just 2 gigahertz, we can multiply 256 into 2. That is 512 gigahertz of the compute available. Mostly on a server class, we have 48 memory slots available or RAM slots available. Even if we go with 64 GB module, so what's 64 into 48? If one RAM chip is 64 gigabytes and we have 48 chips, so can anyone multiply it for me? Probably it's 3 terabyte. Hello?
Yeah, so I got 3,072.
Yeah, that's 3072 or 3 terabyte. So our RAM is 3 terabyte and we can go up to 6 terabyte per machine I am talking about. So which application takes 6 terabyte? None. So the CPUs are 512 gigahertz. The RAM is increasing way too fast. And our application is not using even 1 to 2% of the physical resources. So this virtualization concept came. But the problem with type 2 hypervisor is we all know that the Linux machines are very stable. We don't need to restart them very often. Maybe we don't need to restart them for years. So the problem is if we are running the base OS like Microsoft Windows and we are running virtualization on top of it, we all know that if we install a driver, we may install an app and Windows need to reboot. Or maybe if the Windows is running continuously for nowadays, this Microsoft Windows 2019 is very stable. But before that, when Windows 2003 was there, when 2008 was there, you have to reboot a machine if you don't know what's wrong. If logically something is logically everything is right, but your OS is not behaving correctly, so you have to reboot your machine. So if the base OS is unstable, it doesn't matter if you're running a very stable operating system on top of it. So if you have to reboot your Windows machine, the hypervisor will be closed automatically. So then came the type 1 hypervisor, that's called the bare metal hypervisor. Zen, KVM, ESXi, and there are many more. ESXi, that is by VMware. Then we have Zen, KVM, and many more. So because the corporate world is dominated by VMware, so we are discussing VMware here. And let's discuss type 1 hypervisor. So again, this is our hardware. Before we had an operating system, then we had a hypervisor, and then we have again an operating system of some VM. So this was like type 2 hypervisor. On type 1 hypervisor, this hypervisor is installed on the hardware. It has its own kernel. Okay, the hardware is, let's say, CPU. we have RAM. We may have network. We may have disk inside this box, or we can have disk outside this box. We will discuss that later. So it has its own kernel, its own operating system, which is mostly a very fine customized Linux distribution. There are no extra packages, just very minimum operating system with a minimum footprint, and it is installed on the hardware. And the VMs are directly managed by this hardware, this esxi. And we create VM on top of it. If we are using the hard disk here, when we create a VM, okay, let's discuss that later. The concept is clear for type 1 and type 2 hypervisors, right? So let's go with the disk part. Our CPU is divided among all these VMs. Our RAM is divided. Our disk is divided. Let's discuss the disk now. So what about disks? Before, in earlier days, we had even 1 gig hard drives. Then we went on with 100 gigs. Then we went into the terabytes. So the disks are also virtualized in this virtualization technology. So we have concept of thick, thin, and we have further categorization of eagerly zeroed and just the plain thick. So mostly we go with the thin drives. We have created VMs, and I asked you to create a thin disk or don't allocate space right now. In type 2 hypervisor in VMware, it asks you to allocate the disk now, or you can go with the thin. So what happened is we have, let's say, 100 GB hard disk available. We present that 100 GB hard disk to our hypervisor. It formats it in its own, like in for VMware, it is VMFS. It's the file system, VMware file system. It formats it. And when we create a VM, let's say we have 100 gigs available to this partition, formatted through VMFS. And we are creating a VM, which is, we are giving it a hard disk 100 GB for VM1. For VM2, we are again giving 100 GB. And for VM3, we are again giving 100 GB. So we have total 100 gigs available, and we are giving all 3 VMs 100 gigs with thin provisioning. What happened is, when we install OS, maybe if we are installing the Linux distribution with minimum packages, the footprint is just 400 megabyte. So in thin provisioning, when we install the operating system, we have said machine that you are given 100 gigs of space, and this 100 gigs is available to this operating system. But on the back end, what we are doing is we have done it thin provisioning. So when we start installing the operating system, it will start writing the data on this bigger disk. So if the installation is 400 MB, we have just used 400 MB of the space, and we only write 400 MB to our backend disk. The operating system will see it 100 MB, this VM. It will see it because we have presented 100 GB to this operating system. But when it wants to write to our VMDK file, the VMDK, which is the extension of hard disk in VMware, this is a file created on our main hard disk. So it starts growing when the data is coming to it. And let's say we install VM2, so it will take some space, let's say 1 GB. And VM3 can take, let's say, 2 GB out of this 100 GB. And when we write something on that virtual machine that is actually written in a file called vmdk, and that is simulated as disk. So if we have 100 gigs available, we can provision 300 gigs or 400 gigs. It depends how much actual data we are writing to the virtual machine. Any confusion in this?
No.
No.
Can you so in what scenario would you choose thick provisioning?
For databases.
Okay.
Because
So in a,
yeah, sorry.
so in like regular environment, like when you boot up a machine in VMware, you just use thin provisioning.
We use thin provisioning because that's the only beauty of virtualization or cloud. Actually, on the cloud is what? It's an abstraction, or it's an orchestration layer over virtualization. When virtualization came into the market, it was just for the organizations. Well, I mean, it is on-prem only. You can create a VM, you can destroy a VM, you can have a network, and then the orchestration layer came in that why not? We have so much hardware available. Why not distribute this hardware, isolate this hardware and distribute this hardware into tenants? And then the orchestration layer was deployed on top of virtualization, and it became the cloud. And then it expanded. I mean, we had so many things on the cloud. We had the load balancer. Everything is now on cloud, and everything is like software based. So the base for every cloud is this virtualization and these concepts. We are doing thin provisioning hard disks. The beauty is we are selling VM1, VM2, VM3 to our customers. Everybody is asking 100 gigs of space, maybe 200 gigs, maybe terabyte of space. But we know if I am buying a laptop, let's say the space is 1 terabyte, we know we will not fill up the space in one day. We will gradually fill up the space. But we have to pay for this for that 1 terabyte disk. So for operating system, at least everybody will ask 100 gigs of space, but it is using actually, let's say 20% of the disk. So rest of the 80% is free, and the customer is paying for it. So this was a very successful model. So everybody quickly shifted to virtualization, and the other advantages are that we know what snapshot is. You can take snapshot, you can take clones. So management became too easy. And we will discuss further scenarios, what advantages this platform is giving us. So we know how CPU is over provisioned. We know RAM is over provisioned, and we know disk is over provisioned. But the problem is, if this guy is using now 50 gigs, and this guy is also using 50 gigs. So what happens is he has used his 50 gigs, the other has this 50 gigs used, because actually we had 100 gigs available. So this guy cannot write it anymore. And if this guy will go to 51, it will not be able to write to the disk. And maybe either it will stuck, maybe your application crash, maybe your OS can crash. So you have to very carefully plan that what's the trend of your growth, how much data your customers are writing to the disks, and you should know your procurement cycle, so that you should initiate your procurement way ahead, so that till this stage is reached, you buy the new hardware and you install it, right? Okay. In the real world scenarios, we don't go with a single host. We have multiple ESXi servers available. This is my one server. One is ESXi machine. This is my second ESXi machine. This is my third ESXi machine. We have CPU.
On the same server?
No, these are all three different servers. Physical separate machines. It has its own CPU, it has its own CPU, it has its own CPU. We have separate RAMs available. And we have very small, maybe 32 GB or M2 SSD chip available these days. Or if that is not available, you can install 2 hard disks here. and implement RAID over it. We will discuss RAID anyways. Let's assume we have 2 hard disks available, and we mirror those hard disks and make logical one hard disk through some technology. So if one of the hard disks is crashed, your operating system is not crashed, and it will continue running from the second hard disk, because they are logically, there is logical one hard disk, and these 2 hard disks are mirroring their state. And on this hard disk, we install the esxi only. So the only hypervisor is on this hard disk. And when we create a VM, we have very big shared storage. And this storage, let's say I have 10 terabyte volume. We present this 10 terabyte volume to this machine, same volume to this machine, and we present the same volume to this machine. And we mount it in their operating system. So let's assume we have mounted it on, let's assume /disk1/disk1/disk1. We are mounting it using any protocol, maybe esxi, esxi, NFS, whatever protocol is supported by our storage. So if I am creating my VM here, what happen is the storage is, let's say we created a VM1. So this VM1 is actually created here on this volume. It is installed on /VM1, but actually we know this disk is mounted from this shared storage. So whatever is there is actually present here. Nothing is physical there. If we unmount this storage, nothing will be there on that esxi host. Do we agree?
Yes.
On the second one?
No, on the.
Let's continue. On our first machine, this is our first server, this is our second server, this is our third server. So if this same disk, same 10 TB is available here, it's available here, it's available here. And whatever we are writing here to VM1 is actually present on the shared storage. And as this 10 TB is also visible to these 2 guys, they can see whatever is there in VM1 folder also. So let's say if this host is gone, crashed, powered off, whatever happened, what we can do is we can boot that virtual machine from this physical server. Why? Because this 10 TB is available here. This VM1 folder is available here, and we can boot the machine from host 2. All the data is available here on the shared storage. And the CPU, RAM, and the network is used from this. These resources are used from the esxi hardware, and the storage is used on the shared storage. So when this host is gone, this VM will be booted up. It will use the CPU, RAM, and network of this physical host. And storage, obviously, it's coming from the shared storage. Any confusion in this?
No. Right.
No. So it's pretty awesome stuff. Let's assume we have 100 VMs running on this machine, and we have only 2 VMs running on the, we have 2 VM running on the third node. So for host 2, we are using so much resources, and the host number 3 is free. So what we should do is, we have VM1 running. On the fly, we can migrate our VM from this host to this host. The operating system will remain powered up, your network will remain powered up, your users will remain connected, and on the fly, you are migrating your virtual machine from one physical host to the other physical host. It's like you have a laptop, you are working on it, and somehow everything goes to another laptop and you don't feel anything, right? So that is called migration. We can migrate VMs from here and there, and they are actually done automatically. There is a tool in VMware which is called DRS, dynamic resource scheduling. It always observes the states of the resources, and if one, let's say there is a customer whose VM suddenly starts taking more resources, more RAM, more CPU, so there is a congestion on the host. So what DRS will do is it will migrate few of the VMs to any other available host which has some less resources utilization, and maybe it will send it to multiple hosts depending on the cluster size. And that's how we actually, the machines are always moving here and there, and the user doesn't know what is happening in the background. So the first advantage is we are over provisioning. The second advantage is we are optimizing the resources on the host. The third advantage is high availability is achieved. Let's say if this host is gone, you can restart the machine here. So at least your downtime is very minimal. You don't have to install the complete operating system, the application and everything. You will just boot the machine and as the host is already gone. So the power up time of a VM can be less than 1 minute. So the downtime is only 1 minute. And we all know that for a critical application, we are running everything behind a load balancer. So let's assume I have a host. Okay. We have our VM and we have our VM. This, come on. This can be our database master. And this can be database slave. Now, maybe these are two hosts. And there is a lot of workload running on these two machines. There can be a scenario that this VM is migrated here. And if this host crashes, your master and slave, both databases are gone. You can reboot them, but the state can become inconsistent, or at least there is no point of having two databases running if you are having a downtime. So what you can do is we have affinity rules. We can define that these two VMs, they cannot remain on the same host. They should always be on different nodes, so that if one node can go down, the other one database or one physical node can go down, another VM is running on some other host. So this is called anti-affinity rule. And we can club the virtual machines together. That's called affinity. Let's say in some scenario, I want to say that if this machine is migrated to host 2, along with this machine, which can be a second virtual machine, this should also go to host 2, because these two machines will remain together wherever they will go. So we can define affinity and anti-affinity rules, and we can force the VMs to be on the same physical host, or we can force them to be on different physical hosts. So this is one more concept of virtualization, and it is present everywhere. Now, let's go to the network part. We know how we are using CPUs, how we are using RAM, how we are using disk, the shared storage. And shared storage are very resilient, very huge, and very robust hardware, and very expensive. So let's go back to the network part. I have a physical box available. There can be so many scenarios. It can have 1, 2, 3 NICs available, NICs, network interface cards, or your Ethernet cards. And definitely, we have networks available in our data center. We have switches available. We have firewalls available. We have physical load balancers available. So basically, we have physical switch available. You know what switch is?
Yes.
Everybody knows what switch is, right? We have switching devices available. This host is connected onto this port, sorry, this NIC card, and this NIC card is connected on this port. Maybe this is connected on a different switch, and this should also be on the same switch. So the networking for all the hosts should be exact same, because what we are going to do is we are not discussing VLAN here because I don't think everybody is from IT field. So let's assume that this is one section of a network, and every machine in this section can communicate to each other, and there is some different section, and all the VMs in this section, this black section, they can communicate to each other, but they cannot communicate in between.
Well, because it's on a different VLAN, right?
Just because of the concept of VLAN. Actually, I'm not going into VLAN, otherwise I have to explain that too. But let's say on this physical NIC, we have a virtual switch available, just like this physical switch. And for this NIC, we have another virtual switch available, because when we create a VM with CPU, RAM, and disk, this VM requires a network also, the NIC card. So the NIC card can be connected to this virtual NIC, and for this VM, it can connect to this virtual switch. And this virtual switch can go to firewall. It can connect to firewall. It can connect to firewall. Maybe through firewall, you can allow the policies that this machine will come to this virtual switch. It will go to this physical switch. From there, it will go to firewall. And from firewall, it can come back and talk to this VM. Maybe you can allow only they can talk to each other on port 420 to port 80 or whatever the policy is. The point is, when we create the virtual switches, they have to be same on both the hosts. Why? Let's say I call it switch 0 and I will call it switch 1. So it should be exactly same name, switch 0 and switch 1. Because when we are creating a dot VMX file, and the amount of CPU we are giving to the virtual machine, the RAM we are giving, the hard disks we are attaching, the network we are attaching, everything goes into that VMX file. And we all know that this VMX is, along with everything, it is placed in some folder, and that folder is available on the shared drive. If this host is gone, so this physical host will start reading this VMX file. And VMX file will say that, okay, I have this much scores available, this much RAM available, this much disk available, and I am connected to switch 0. So if switch 0 is not available here, it will not be able to connect to this switch. Right? So if we have physical 100 hosts available, What we should have is we have switch 0 configured on those 100 physical machines. If we have switch 1 available, we have to configure that switch 1 exactly on those 100 machines. And let's say by mistake, on any host you did a typo, or maybe on it is small sw1, and on some machine maybe you have write capital sw1, so there is an inconsistency, and when the machine is booted on that host, it will not connect to network. And when we will let's say it is switch 01, and let's say by mistake I am using capital S here, so I cannot migrate this VM to this host because it will say switch 0 is not available there. So this is a problem, right? Any idea how to solve that problem? For that, I'm not going into the detail. For that, there is a concept of distributed switch, and maybe I can show you, or maybe I will not. This is a concept of distributed switch, but that distributed switch is only available when we have a layer vCenter. So it is not possible to manage all 100 hosts individually, going in there, configuring everything. So we have another tool, you can say it, a management tool. All the hosts are imported in this vCenter, and we can view all of them through this vCenter, and we can configure everything through this management engine. And through this management engine, we can create distributed switches. And whenever we create, that's actually called a port group. Let's say it a virtual switch. When one distributed virtual switch is created, it is created automatically on all the nodes available in the cluster. So that's how we solve the problem of creating the network on every machine. We create a distributed switch, and the distributed switch handles every network component.